Welcome to this explainer. Today, we're unpacking a really fascinating chapter on physical oceanography. We all know Earth is dominated by water, right? But so much of the massive planetary engine that actually drives our world is completely hidden right beneath the waves. So, we're going to explore those hidden landscapes, the extreme temperatures, and the delicate chemical balances that sustain this entire global system.
Okay, let's dive into this. To get a sense of the sheer scale we're talking about, an astonishing 91% of all the water on our planet is held within the oceans. Think about that for a second. Every single river, every lake, every melting glacier, and every cloud you see in the sky combined makes up less than 10%. The oceans are, without a doubt, the undisputed giants of the global ecosystem. Here is our itinerary for today's expedition. First, we'll look at the endless water cycle. Then, we'll be mapping the ocean floor. Third, we'll check out ocean temperatures. And finally, we'll uncover the ocean's salty secrets. Let's start with part 1, the endless water cycle, which is basically our planetary engine. To truly grasp the scale of the oceans, we first have to look at how they interact with the atmosphere and the land. The hydrological cycle is this massive, intricate engine that has been running nonstop for billions of years. Water is a cyclic resource. It's in a continuous exchange between the oceans, the atmosphere, and the land masses through evaporation, condensation, and precipitation. What is absolutely vital to remember here is that the total amount of renewable water on Earth is completely constant. It doesn't change. However, as human demand keeps increasing, we run into water crises, both depending on where you are and what time of year it is. And anchoring this entire life-giving cycle, it's the ocean, acting as our planet's massive reservoir. Moving on to part 2, mapping the ocean floor, let's look at the relief of these massive basins. Imagine, just for a moment, pulling a giant plug and draining all the ocean water away. What you'd reveal is this incredibly rugged topography hiding anywhere from 3 to 6 kilometers below sea level. If you stepped off the continent, you'd first hit the shallow continental shelf, which is famously rich in sediments and fossil fuels. Keep walking and you drop right off the steep continental slope down into the basin, eventually hitting the deep sea plain, literally the flattest regions on Earth. And if you go far enough across those plains, you just might plunge into the oceanic deeps, or the trenches. Now, what's really interesting about this slide is that the ocean floor is not just some flat, featureless bowl like a lot of people assume. It actually features the world's largest mountain ranges, entirely created by immense tectonic and volcanic forces. The ocean floors are incredibly rugged. They mirror, and honestly, they often dwarf the dramatic landscapes we see up here on dry land. For instance, take the seamount. A seamount is exactly what it sounds like, a mountain with a pointed summit that rises up from the seafloor but never actually breaks the surface of the water. They are volcanic in origin and they can be absolutely massive. The Emperor Seamount in the Pacific Ocean, which is an extension of the Hawaiian Islands, is a towering example of these dramatic underwater peaks, rising thousands of meters right up from the deep sea plain. Then we have something called guyots. These are essentially seamounts whose tops have been flattened out by gradual subsidence over time. And the scale of these formations is wild. Get this, it's estimated there are more than 10,000 seamounts and guyots in the Pacific Ocean alone. Atolls offer a totally different kind of structure. These are low, tropical islands made entirely of coral reefs surrounding a central depression or a lagoon. They form this really unique ring of enclosed water right smack in the middle of the open sea. And alongside those mountains, the ocean floor features some incredible chasms. You have submarine canyons cutting right through continental shelves. To put that into perspective, the Hudson Canyon is as grand as the Colorado River's Grand Canyon. And then there are the deep trenches, which are closely associated with active volcanoes and strong earthquakes. As many as 57 of these oceanic deeps have been explored so far, 32 in the Pacific, 19 in the Atlantic, and 6 in the Indian Ocean. They are vital windows for scientists studying tectonic plate movements. All right, let's head into part 3, temperatures of the deep. It's time to shift our focus from the rocks back to the water itself. If we symbolically fill the oceans back up with water, we need to look at how that water behaves. Just like the land, ocean water is heated by solar energy, but its temperature is nowhere near uniform. Surface temperatures naturally drop as you move from the equator out toward the poles. Plus, it's dictated by unequal land distribution, prevailing winds, and massive climate-regulating ocean currents.
For example, the warm Gulf Stream acts like a heater, raising temperatures off the east coast of North America and the west coast of Europe, while the cold Labrador Current chills the waters right off North America's northeast coast.
So the crucial point is that the ocean actually operates in very distinct layers. If you were to dive straight down, the water doesn't just gradually get colder. Actually, between 100 and 400 meters below the surface, you hit this harsh boundary region known as the thermocline. In this specific zone, the temperature plummets incredibly rapidly. The thermocline acts almost like a solid wall between the sun-warmed surface water and the freezing pitch-black depths below. The resulting math here is staggering. Only about 10% of the ocean's total volume is that warm surface water we're all familiar with. A massive 90% of all ocean water sits below the thermocline in near-freezing, complete darkness.
Finally, let's unearth Part 4, the ocean's salty secrets.
To really complete this chapter, we have to look at the ocean's chemical makeup. When we talk about how salty the ocean is, we use the term salinity. It's simply calculated as the amount of dissolved salt, in grams, found in 1,000 grams of seawater. So we express it as parts per thousand. Salinity is basically driven by a constant battle between evaporation, which concentrates the salt, and the influx of fresh water from rain and rivers, which dilutes it. Just for context, a salinity of 24.7 parts per thousand is considered the absolute upper limit for us to call water brackish.
Now, while the open ocean normally hovers between 33 and 37 parts per thousand, some isolated water bodies on land push this to the absolute extreme. The Great Salt Lake hits 220, the Dead Sea sits at an incredibly dense 238, and Lake Van in Turkey, it completely dwarfs them all at a staggering 330 parts per thousand.
But even within the ocean's connected seas, we see huge variations based on geography. Enclosed seas in really hot regions, like the Red Sea, suffer from high evaporation and can spike up to 41 parts per thousand. The Mediterranean also records very high salinity for that exact same reason. Conversely, the Baltic Sea and the Black Sea record very low salinity. Why? Because massive amounts of fresh river water are constantly pouring into them, diluting the salt. And this brilliantly illustrates our final concept, the halocline. Just as temperature creates vertical layers in the ocean, so does salt. Saltier water is naturally denser and heavier, causing it to sink right below lower salinity water. This creates distinct, invisible, stratified layers beneath the waves. The halocline is that sharp vertical zone where this transition happens. So you see, the ocean isn't just some big mixed bowl of soup, it's a meticulously layered cake of temperature and density.
As we wrap up this explainer, we're left with a truly massive question. We've seen how the ocean is this finely tuned, incredibly complex machine. But as climate change alters evaporation rates globally and melts our freshwater glaciers, how will the delicate balances of the thermocline and halocline shift? And, perhaps more importantly, what will that mean for the billions of lives depending on the global water cycle? It's a massive, deeply interconnected system. Keep learning, keep questioning, and thanks so much for joining me today.